Hello. Let's see. Okay, people are starting to enter now. Okay. Okay. Okay, everyone's joining up. So I'm going to go ahead and switch to screen sharing. Okay, you should see a desktop now. Okay. All right. Um, the first, let me point out the homework assignment. I finally got it up there last night. It took me a while to write it. Okay, so if you go over here to the page, the homework assignment has been there since late last night. Okay, let's start off by just kind of quickly going over what's in the homework assignment, and then we'll go back to talking about the render one. Okay, so let me download the zip file. I can unzip it. Okay, and hey, here's your goal. Your goal is to produce this animation. Okay, so you're going to write a program that produces this animation, and you're going to do it with a combination of working with the renderer and then doing something similar to what you did in the first homework assignment. You're going to be working with the frame buffers. So this assignment works with both the scene data structure, which is input to the renderer, and works with the frame buffers. You do something with the frame buffers after the render is done with them. Okay. All right. So let me show you uh, uh, an outline of what you need to do. Okay. First, you're going to create this animation. And this is what the renderer is going to produce. The renderer is going to produce this animation. So your first step is you're going to that's this file here, homework 2 version 1. You'll complete this file to create this animation. Okay? And then this other animation, oh, one of the nice things, I'm using Earthran View to watch these animations. And one of the nice things about Earthran View is when you open a uh, animated GIF file, the G key stops and starts the animation. Okay, so there's three things that you can do in Earthram View that's real useful when you're working with these animated GIFs. First of all, the G key starts and stops them. Okay, now the other thing is when it's stopped, I'll stop. When it's stopped, you can step through the animation. Let's see if I can remember which key it is. I'm holding down the function key and hitting it's the page up key. The page up key, everybody's keyboard has a different way of doing the page up key. In my case, it's function key and the up arrow key, but it's the page up key. This is stepping me back through the frames, then page down steps me forwards through the frames. Okay, so I can just start and stop at any time. I can step through, okay, anytime. And same with this one over here. I can start and stop it. I can step through it. I'm actually, you don't see it so much here. It looks like I'm actually single stepping through the frames. The only thing it doesn't tell you, wish it did, was what frame number you're on. It doesn't tell you which frame you're on. It'd be nice to know if you're on like the 50th frame or the 150th frame. I don't think it tells you what frame number you're on. Okay. Now the third thing it can do, so Earthframe View can start and stop the animation, and it can let you single step through the animation. And another thing you can do is you can blow up the animation. You can blow it up into all the frames that are in the animation. Let's see if I've forgotten now where that was. Let me check real quick. I forgot where that is. Here's start and stop animation. Oh, extract all frames right below it. So start and stop animation, extract all frames. Okay, extract, there's 480 frames in this movie. It's going to create a temp file. Oh, let me put that. It's going to put it in a weird place, in my app data local directory. That's actually not such a great place to put them. Let me go ahead and put them on the desktop. And I'm going to put it in a temp directory on the desktop. Okay. So I'm going to put it in I'm going to put the frames in a temp directory, and I can control what they're exploded into. I'll go ahead and explode them into ppm files because that's what we started with. Okay. So I can explode them into ppm. Actually, that's too. I don't want to wait. Let me just go explode them into PNG files. I'll explode them into PNG files. Okay, and then start. There's the temp folder. And there's frame one. Now, yeah, there's frame one, there's frame two, frame three, well, I'm up to frame 4, 5, 6, 7, 8, 9. Okay, see, there's the individual frames. Okay, but yeah, it's depending on, sometimes you want to check a particular frame, like if you want to know what happened in a particular frame, it's useful to be able to extract all the frames from a GIF. So I keep telling you, EarthFrame View is a great tool. EarthFrame View, I mean, if anybody knows any other program they think is better than EarthFrame View, I'd be interested in knowing. But so far, EarthFrame View is able to do just so much that's useful when working with any kind of graphics. Okay, so the three things that that are, at least for this assignment, three things that are useful for you is, when you're watching this animation, again, you can start it and stop it. You can step through the pages, step through the frames, and if you want to, you can go to, I think it was, you could extract all the frames if you need them. Okay, all right. Now, what's the difference between now? Let's, in the homework assignment, this file is meant to create this animation, and then this file is meant to create this animation. Okay, so these are the sketches right now, so you have to fill in those two files. Okay, so you're okay now. Let me just show you the difference between the two animations. Okay, here's the beginning of this animation, and I can go back to the beginning of this one. Okay, there's the beginning of that one. Okay, so this thing, just what it does is it draws the letters PNW, moves them up, draws the letters PNW, moves them up, draws the letter PNW, moves them up, and those are the frames. So you're just going to draw the letters PNW in, the three letters are in a scene, and you render the scene and save the frame buffer. Then you move the letters up in the scene, render the scene again, and you'll get this next frame. You get the next frame, and then you save that frame. Then you move the letters in the scene, render the scene, get that frame, and you save the frame. Okay, so you get this animation just by rendering a scene, then moving the three letters up, okay, and then after you've moved them, you render again, okay, and then when at some point after you've moved the letters up one unit, then you start moving them to the down and to the right. Okay, then they move down and to the right until they've gone 3 units down, and then they start moving to the left. This screen has the origin right here, +2 here, -2 here, -2 here, +2 here. Okay, and the letters are 1 unit high. So at the beginning, this is 1. This is 1. Yeah, the origin's right here. That's 1. That's height 1, and the letters are height 1, and they go up to the top. So you push the letters up 1 unit. Okay, that's just the starting. Okay, now what's going on over here? Okay, what this guy does is he works with 20 frames of this movie at a time. So each frame of this movie is created actually from 20 frames of this movie. Now at the beginning, there's only 1 frame. So now look real carefully at what's going on over here. There's the first frame of this movie, and it's the same as the first frame of this movie. The second frame of this movie is the second frame of this movie, and if you see in light shadow, it's actually also the first frame of this movie, but lighter. Okay, so what I did was I took 2 frames of this movie and copied them into 1 frame over here. The newest frame here is in white, and the previous frame here is in half white. Now, if I here, I'll advance a few more frames. Okay, I'm at about the 5th frame over here. And what I've done is I've actually taken, from over here, I've taken 5 frames. The first 5 frames, 1, 2, 3, 4, 5. I've taken those 5 frames and merged them into 1 frame, but as the frames get older, they get lighter. This is not done by the renderer. This is what I call post-processing step. The post-processing step is when you take frames generated by the renderer and you do some sort of pixel manipulation on them. Here, you're creating a new frame by merging previous frames together, where each frame gets a little bit light. As a frame is merged, as a frame from over here is merged into this frame, it's made a little bit lighter, a little bit lighter, a little bit lighter. That creates this tail. Oops. This is done up to 20 frames. Okay, if you can maybe try to count them, but there's about 20 frames there, and they're getting lighter and lighter. So that's starting. That would be from over here. That would be the first 20 frames here. This one, this one, this one. So that's like the first 20 frames over here. The first 20 frames from over here have been combined into 1 frame here, but the older frames get lighter and lighter and lighter. Okay, and that creates this trail of frames over here. That creates this trail that you see. And you kind of see that when the letters start moving in the other direction, you can see how the old ones are still going up, the previous ones are still going up while the new ones are coming back down. So you get this effect of a trail. Okay, the trail effect is created by post-processing, by manipulating the frame buffers, not by using the renderer. So the renderer creates this data, these frames, and essentially what we'll do is in the second program will store these frames in a list data structure. So the second version is going to create a list data structure of frames, and then it'll take the last 20 frames from the list to produce 1 frame over here. Okay, so that's the idea, is to do a rendering step and a post-processing step. The rendering step using the renderer, and the post-processing step just manipulating frame buffers. Okay, now let's look more carefully at the first step. Okay, the first step needs a P, N, and W model. Okay, you need a geometric shape that's a P, an N, and a W. So there's these 3 files here. This is what we've been talking about for the last couple of days, creating models. We're going to do more with that today. We're going to go back and look at this in more detail. the class P is a model. P is a model. There's the vertices in the P, and there's the line segments in the P. Okay, now I made the P for you, and you have to do the N and the W. Make your own N and make your own W. Figure out what vertices to add, figure out what line segments to add. Draw an N and a W on a piece of paper, and just like figure out what points you need. Like, that's how I did P here. You can kind of, the letter P sits in a square that's 1 unit by 1 unit. So the lower left-hand corner of the P is at the origin. Its lower left-hand corner is at the origin. And then, starting from the origin, I drew a letter P in a 1 unit box, and then figured out where the point should be, just by kind of like just eyeballing them. Okay, you need to do that with N and W. Make your own N and make your own W. Okay. All right. So then when you have these letters, then you can go and create I sketched some of the code here for you. Okay. So to create a movie, we're going to use an 800 by 800 width frame buffer. So there's the frame buffer is going to be 800 by 800. So I made those static variables so the whole program has access to them. We want clipping to be turned on in the renderer. So I did that just because it's easy to forget to do that. And if you don't, then the renderer blows up when you go off screen. Okay. All right. So I just set that so that it would be there for you. Okay. Create a scene object. Add PN and W to the scene. Okay. This is the code. We want to push them away. Notice that when I created the P, I put it in the XY plane. Everything's flat. This is not really a 3D project. It's really 2D graphics. So the letter's flat in the XY plane, but the camera's in the XY plane. So you have to be in front of the camera. So this step here pushes all the models 2 steps behind the camera. When they're 2 steps behind the camera, that's why the view volume goes from the origin here up to 2, down to -2, over to 2, and to the right 2. Because this is actually the z equals -2 plane in the view volume. And the view volume, as we said the other day, it's got a 90-degree field of view. So that means let me show you. No, not that. I don't think I drew this picture. If you have a 90-degree field of view, okay, so here's an X. There's an X-axis and Y-axis. Okay. A 90-degree field. Now, suppose you have an eye. Actually, make this the Z-axis, so you're staring there. What's a 90-degree field of view? To get a 90-degree field of view, you would have a 45-degree line out this way and a 45-degree line out and 45-degree out this way. I didn't draw it very well. Now that's 90 degrees. But this is the line y equals x. This is just the line y equals x. And this is the line y equals -x. Okay. So if you go over here to -2, so if you're here at -2, actually, yeah, this is actually the negative z-axis, so I actually got this backwards. This one would be y equals x, and this would be y equals -x. It just, yeah, but, or if you want, you can just think of this one as 2, not -2. But then you're 1 unit across here. I'm sorry, you're 2 units over to here and 2 units over to here, because these are 45-degree lines. So if you go up 2, you go over 2. Okay. Going across here is going across this. Here, if this is the if we think of this as the z-axis, and this is, say, the x-axis here, in this picture, the z-axis is pointing straight down where the mouse is. The z-axis is pointing out of the screen where the mouse is. So you take the picture on the left and you lay it flat, okay? And then, the x-axis is this way, the z-axis is going down the screen. In this picture over here, the y-axis is coming out at us out of the screen. But then when we lay it down over here, the z-axis goes into the screen. So then, since our field of view is a 90-degree field of view, its edges are two 45-degree lines. If you go back 2 units, you have 4 units across the view rectangle. So when you go back 2 units away from the camera, you have 4 units across the screen. That's what we have over here. 4 units across the screen here and 4 units across the screen here. So that gives you a sense of the space you're working in. Okay, then you move these letters around in that z equals -2 plane. Okay, okay, all right. So this is the thing that pushes everything back from the z equals 0 plane, where they're on top of the camera, to being 2 units behind the camera. Okay, and that gives us a 4 unit wide by 4 unit wide stage to move the letters around in. We essentially have a 4 unit by 4 unit stage. Okay, right. Then I move the models to their initial location. Here's where the models are initially. Okay, there's the initial place of the model. The P has been moved to the left 1.6, the N is moved to the left half, and W is moved to the right 0.6. So this letter would start, this is 0 in the model. This lower left-hand corner is 0 in the model, but now it's moved to here. You would make this 0 in your N model, but then it gets moved to here. And well, the 0 in your W model will be right about here. That's where the origin would be in your W model. You probably wouldn't want it to be here. You could. If you make this your 0 in your W model, your W will probably touch the N. You could fix that by moving W over here. Or you could just make it so that the 0 of W is right below the top. That'd be the better way to do it. Make the 0, the origin of W would be below that left-hand edge of it. Okay, so then it's moved to 0.6. So this would be 0.6. Okay, now remember, this is 2 over here, and the 0 is right in the middle of the screen. 0, that's about 0.6, 1 is about here, and 2 is over here. Okay, so the letters are, I put the letters in their initial position here. That way everybody kind of starts at the same place. If I thought about having you figure out where to start the letters, but then I thought if you're off a little bit, then the whole animation's off a little bit, and it'd be hard for you to track down if you got something right or wrong. So I thought it'd be better for me to place your letters initially so everyone's placing them at the starting. Everyone starts off in the same place. Okay, then here's the loop. Then create a frame buffer that you're going to keep refilling. So there's a frame buffer, and the animation is going to keep refilling it over and over again. Here's the loop that creates the animation, empties the frame buffer, renders into the frame buffer, dumps the frame buffer, updates the scene. Okay, you have to write update the scene. Okay, update the scene is right there. You have to figure out how to move the models. Okay, so you write update the scene, and down here I point out that you might want to have a move models and a move model method. Update the scene. Like here, move model, I already used it here. So you get a sense of what I meant there. Instead of writing this loop here, which move the models, this is what you don't want to keep writing over and over and over again. So I'm giving you a hint that what you really want to do is take this and break it down into move models and move model. Move models will call move model. Okay, so it's really, the code's right there, but you don't want that block of code to be repeated over and over and over again. And, and notice that these only take a delta X and a delta Y, because everything's done in 2D here. That's actually why I didn't call that method here, because this is actually moving it in the Z direction. Okay, I wrote the code here more or less to show you what it looks like, But this code couldn't use those methods because here I'm actually moving in the Z direction. I want to push things away. These only move by that much in the X direction and by that much in the Y direction. So everything is happening in, the motion is all happening in 2D. Everything's just moving left, right, up, and down. Okay, so you have to write the update scene, move models, and move model. Okay, and then you get this movie here. Okay, and you notice that there is you're told here 450 frames, and you have to break this down. What you really need to do is break down update scene by which frame number you are. So you have to do a little bit of thinking, like if this we get to the beginning. Okay, there's the beginning. Okay, so you have segments: a go up segment, a move down into the right segment, a move left segment, a move up into the left, then another move left segment, and then a move up and right segment, and you're back to the beginning. Okay, so you have to break down this update scene by frame number. You know, it's going to be a bunch of different ranges of frame numbers will tell you which motion you're moving in. You know, depending on the value of the frame number, you're either, that you're at the beginning you're moving up, later on you're moving down into the right for several frames, and then for another number of frames you're moving to the left for a number of frames, and then you're moving up and to the left for a number of frames. So that goes into the update scene. You have to break this down by what frame number you're at, and then that tells you how to move the models. Okay, so you move the models in a way that depends on the frame number.
Wouldn't it be better to create a state machine instead?
Say again?
Frame number.
I couldn't hear you. Say it again a little bit louder.
Wouldn't it be better if you could create a state machine instead of using the frame number?
Good question. If you want it, okay, yeah, if you want to try it that way, that might work better. Yeah, but yeah, I mean, you could probably write the code a little bit more efficiently as a state machine, because there's like what is it, 1, 2, 3, 4, 5, 6 states. Okay, so there's 6 states. Yeah, so you could change update scene to be, you might even put it inside update scene, however you want to do it, but you could do it as a 6-state state machine. Yeah. Okay, so that'd be another way to do it. It might even end up being a little bit less code. I'm not sure. You definitely could write it that way. I'm not sure if it'll end up being less code or not, though it might make it easier to think about it. Okay, so that's good. That's not a bad idea. Okay. If you want to redo this code, you can redo this code. If you can think of a better way to organize the frames, go ahead. This is kind of a suggest. So I should put, this is a suggestion. If you can think of a better way to organize these frames, go ahead. Okay. All right, now to the harder part. The next version. This one that creates this movie here. Okay. What it's going to do is okay. This length here, 30, is actually how many frames are in the tail here. There's actually 30 frames in that tail. There's actually 30. Now, earlier I said 20, but yeah, later I changed it to 30 to give it a longer tail. The last few get pretty dim. There's a few down here that you can barely see them, but it works out kind of nice. So there's 30 frames in that tail. So that's this global variable here. It controls the length of that tail. Okay, then the beginning of the code, this part of the code is all the same. Okay, that's all the same. Okay, now here's where it starts getting different. We're going to create a list of frame buffers. Okay, and then at the beginning of the movie, you have to fill in. Okay, right now what you're going to do is you're going to create that frame and put it in the list and draw it. Then you're going to create a second frame and put it in the list and create a new frame that's a combination of those two frames. Then you're going to create a third frame, put it in the list, and then create a frame that's a combination of those three frames. Then you're going to create another frame, put it in the list, and create a new frame. Now, I'm using the word frame in two ways. There's frames you put in the list, and then frames that you're going to draw. So you're actually producing frames to put in the list, and the frames you put in the list are the same frames that we generated in the other renderer. But then you use the frames in the list to create a frame that you draw. And then here's the line of code that creates the frame that you draw. We'll look at that in a minute. So the logic is, now notice here we're building up. We haven't gotten to 30 frames yet. So at some point, I actually have 30 frames already. By now, there's 30 frames in here. So now what I'm doing is in each step, what I do is there's 30 frames and it stays 30 frames. So when I want to make the new step, I take the last frame out of the end and recycle it and create a new frame at the beginning of it. So think of this as a list. This is the tail of the list. This guy here in front is the head of the list. That's this list over here. When I want to make the new image here, I start off by taking that frame that was at the end. It's going to drop off the tail, move it up to the front, and render into that frame. So I render the PNW into that new frame, then add that frame at the beginning of the list. Okay? So first I fill up the list. That's these steps here. That's this sequence here where the list is filling up. That's this stuff here. That's when the tail is growing. At the beginning, the tail is growing. Then when the tail has got to be 30 units long, at that point, you're in a second phase where for the rest of the movie, the tail stays 30 frames long. Okay, that's this next loop here where you're cycling through the frames. Okay, then if you go over here, eventually you'll get to the end of the movie. You get to the end of the movie. And the tail starts shrinking. See, this image here stays put, and what I'm really doing is I'm just shrinking the list. I delete the tail of the list and redraw this picture. Delete the tail of the list, redraw this picture. Delete the tail of the list, redraw this picture. And as the list gets shorter and shorter, you get less and less of a tail in here. Like right now, it looks like there's 1, 2, 3, 4, 5, about five frame buffers in that one frame. Okay, and the front frame buffer is the brightest. The next one is a little bit dimmer. The next one's a little bit dimmer. The next one's a little bit dimmer. Okay, so there's 3 phases: filling in the list of 30, cycling through the list of 30, and then emptying the list. Okay. The hardest part is this method called post-process, which takes in the list of frame buffers and it produces a new frame buffer that I dump. So I wrote a tricky little line of code here. This method takes in a list of frame buffers and it actually returns a frame buffer, which is immediately dumped. If you go down here, you have to write this method, post-process, which takes in a list of frame buffers called frame buffer list, and it returns a frame buffer. And I wrote 2 lines of the code. You create an empty frame buffer. You will fill it in with the shadows of 20 frames from this list, and then you return the frame buffer. So here's where you use the, whoops, I'm hitting all kinds of keys. Yeah, see, there's 30, there's a list of 30 frames. This is an example where this thing here would be a list of 30 frames. The frame that holds this P is at the front of the list. The frame that holds this P that's real dim back here would be at the tail of the list. And you have to merge those 30 frames into one frame, where the first frame is bright, the second frame's a little dimmer, the next frame's a little dimmer. And what you do is every frame, every pixel is either black or white. There's nothing else in the frames. In this list, every frame has only black pixels or white pixels. So you copy the white pixels to this guy. So you go through this whole frame. You take one frame out of this frame buffer list. You go through the whole frame using 2 nested for loops. Look for white pixels. If you find a white pixel, you copy it into here, but you have to dim it. So, depending on how far in the list, you dim it by how far back in that list you are. If you're at the front of the list, you copy it full strength. As you go through this list, the pixels from that list get copied into this frame buffer, dimmer and dimmer and dimmer. Okay. And when you get to the last frame buffer in this list, you're painting a pixel with intensity about 0.1. Remember the intensity here would be 1. So the intensity of this last one would be about 0.1. Okay. And you want to scale from 1 to 0.1 in steps. Okay. And remember, there's 30. The number of steps would have to do with the length of this list. You have to step from the front of the list. Make it just decrease the intensity from front to back in 30 steps, or however long the frame buffer is, because at some point the frame buffer won't be 30 long. Remember, at some point, at the beginning and the end, the frame buffer is not 30 long. When you get to the end, the frame buffer might be less than 30 long. I'm sorry, the list of frame buffers might be less than 30 long. See, the list is not 30 now because it's shortening. Okay, but you still want to decrease these images proportionate. So if there's only 5 of them, they would decrease from full brightness to about 0.1. The dimmest one should be about 0.1 intensity. Full intensity is 1.0. The least intensity is 0.1. Oh, remember we said that pixels can be represented by either an integer. Remember we said that, like, you look here at the constructor for colors. You can construct a color using floats or ints. If you use ints, they're in the range 0 to 255. If you use floats, they're in the range 0 to 1. Sometimes you use ints, sometimes you use floats. In this example, use floats, because it's a lot easier to scale floats than it is to scale ints. This is why we have both of them. Sometimes ints really work well, sometimes floats really work well. This is a good example where it's a lot easier to talk about these pixels in terms of floats between 1.0 and 0.1. So the dimmest one would be about 0.1, and the brightest one will be 1.0. It's a lot easier to just scale. It's a lot easier to scale a float than it is to scale an int. Okay, so sometimes ints are nice, sometimes floats are nice. In this example, you'll want to work with color objects as float, float, float. Okay, so it's just easier to scale. It's easier to have 30 float values between 0 and 1 than it is to have 30 int values between 0 and 255. Think of it. I mean, what kind of a pain would you want to do to find 30 integer values evenly spaced between 0 and 255? Okay, a lot easier to find 30 float values evenly spaced between 0.1 and 1.0. Okay, so use floats for your color values in this example here instead of the integer. This is a good example when the floats work better than the integers. Okay, so here's a little sketch of what you need to do there. Okay, I gave you the, yeah, you're going to fill in this new frame. That's the one that gets drawn here. The one that gets returned here is the one that's going to be dumped. See, what gets returned by post-process is what gets dumped to the file system. So that's the frame that the movie's actually making. The frames that the renderer makes, like here, the frames the renderer makes get put into the list. You don't dump them. So this is what we mean by a post-processing step. Now in the first version, you'll render a frame into the frame buffer and dump the frame buffer. See? So you'll render to the frame buffer and dump it. Now you will render to the frame buffer and then add the frame buffer to the list to be processed later. So the render's frames don't end up being, they're not what gets saved. It's the post-processed frame buffers that get dumped to the file system. And this is in the real world, this is a lot of what movie making is. The renderer creates frames, but the frames that the renderer creates aren't always what you see in the movie. Quite often, after a frame is created by the renderer, some special effect will be added in by what's called image processing that maybe can't be done by the renderer itself. The renderer can't always do every step. So like this tail here would be kind of hard to do with the renderer. You probably could do it strictly using the renderer, but I think this is way easier. And even if you wanted to do this with the renderer, you couldn't do it with renderer 1. You would need a more sophisticated renderer to create that effect with the renderer. But it's actually not too hard to create that effect with a post-processing step combined with the render. And that's what a lot of computer graphics systems do. They have a render, but then once a frame has been produced by the render, you can do anything you want to the frame. So you can do all kinds of special effects on the frame. Essentially you can Photoshop the frames. The post-processing steps are essentially like Photoshop steps. You're manipulating the image in one frame. Okay, so there's nothing to stop people from generating a frame using a renderer and then doing a Photoshop-like step, a post-processing step on the frame. And in our case, the post-processing step is combining several frames. You could do a post-processing step that just manipulates a frame itself, or you could do a post-processing step that combines several frames somehow. In this case, we're combining frames. Okay. This is kind of what people sometimes refer to as motion blur. This is like a baby version of motion blur. Okay. In real movies, when things are moving fast, they're slightly out of focus. Okay. And that's because cameras can't actually, unless you have a super high-speed camera, cameras slightly blur things when they're moving fast. And actually, our eyes are used to that. So rendering systems have to create that as a special effect. A movie camera creates motion blur by default. A graphic system like Pixar has to create motion blur with an algorithm because the render itself won't do motion blur. Okay, so this is kind of like a baby version of motion blur. Okay, I think we stepped through all the code in here. Anybody have a question about this two-step process? Create the movie and then post-process the movie. A lot of what I just said is explained in here. So read this real carefully. I tried to, it's sketched out here, and it's sort of sketched out also a little bit in the code. Okay. And there's one last thing. When you write your code, you get a bunch of movies. Okay. You'll end up with this list of frames. Yeah. You'll end up with this list of frames. See, you'll end up with this list of frames. Actually, let me go back and do something again to show you what I want to do. So let me delete this. Let me take this movie. I'm going to blow it up again. But I'm going to extract the frames as PPM files this time. So this time I'm going to extract them as PPM files. Okay, now the PPM files, okay, they got extracted. Notice it was faster to extract them as PPM files. Now I'm going to put them back into a movie. Okay. See this little batch file here? In the homework assignment, I ask you to download something called ImageMagick. Okay. And this is a portable version of ImageMagick. You download this zip file, unzip it, and stick it on your C drive. Okay. So there, I got two versions. See, you can even have as many versions as you want. That's an older version. That's the most recent version. So you unzip that zip file and just stick it in your C drive. Okay, that's ImageMagick. ImageMagick is an image processing program that's used by a lot of people. It actually comes from the Linux world, but there's a Windows port of it. It does all kinds of neat things. You know, it does magic with images, whatever. Okay, so it's a command line image processing program. It's not an image processing program like Photoshop. It can do anything Photoshop can do, but it's command line driven. It's mostly used as a tool for post-processing because it's used to post-process images using scripts. Okay, so it's a kind of useful little tool. Okay, so put that on your computer, and then after you have your frames, what I'm going to do is I'm going to copy this batch file into that folder. This batch file calls the convert function in ImageMagick, and it converts a sequence of ppms into an animated GIF. So it'll create an animated GIF for you. Okay, so that's what this command does. It, you know, there's some parameters in here, but it converts a sequence of ppm files into an animated GIF. Okay, so if I now double click on this, oh, I have to change the way I name them. I have to just take all the ppms. Okay, so now it's working. It's still working. Notice it hasn't, or did it complete? No, it's still working. It's building this GIF here. It's taking a while for it to work. It's building the GIF. It has to work. It has a lot of work to do. There's 400 frames to pack into the GIF file. If you notice, it's a well-written program. It's using all my cores. It's running in parallel on all the cores, trying to, try to create the animated GIF. It's got quite a bit of work to do. So it's running on all the cores. There, okay, finally finished. And now I turned it back into a movie. See? That's what you're going to do. You're going to make, when you're done, you'll take your frames from the second movie and turn it into an animated GIF and submit that. Because I just want to see that you can make a movie out of your frames. Okay. So that's another post-processing step, but we don't do that step. We let ImageMagick do that. Once we have all these frames, they can be packed into an animated GIF by ImageMagick. Okay. So when you run your version of this, it'll produce a bunch of frames, and then you'll have a whole bunch of frames in this folder, and then you double click on the ImageMagick command and you create an animated GIF of your movie. Notice that this image is only, notice that this one is only 1.5 megabytes. But this one got a lot more information in it. It's actually kind of big. It's 15 megabytes. Yeah, because there's so many more pixels in this movie than there is in this movie. There's the same number of frames, but there's a lot more pixels here. So it ends up being a lot bigger of a file. This GIF file is not small. It's 15 megabytes versus this one just being 1.5 megabytes. So all that pixel information shows up in the animated GIF. The fact that there's way more pixels, way more pixel. The animated GIF is a compressed file. It's compressed, but this one compressed a lot because it's full of empty space. So this one compressed a lot. This one didn't compress all that much because it's actually got a lot of stuff all over the place. So there was less chance. The compression algorithm didn't work as well on this one. So you ended up with a file that's not as compressed as much. What you have to do is you have to compare that to how big this guy is. This file here is almost a gigabyte. See, all these, each one of these is 2 megabytes. Each frame by itself is 2 megabytes. This 800 megabytes got compressed down to 1.5 megabytes. Okay, so 800 megabytes of PPM files got compressed down to 1.5 megabytes of animated GIF. That's a lot of compression. Okay, but it didn't work as well on this one. Here, 800 megabytes is going to compress down to 15 megabytes. The size, if you blow up this movie, here, here's a puzzle. This has got more information in it, right? Okay, I'll blow this one up into a different. Okay, so there's that movie, and this one is the other movie. Remember, this one compresses down to 1.5 megabytes. This one compresses down to 15 megabytes. This one starts out as 800 megabytes. This one starts out as 800 megabytes. Why do they start out the same? If this one's got more information in it, why does it start out the same size as this one, which has less information?
Haven't taken any of the redundancy out yet?
Because they're what kind of files?
PPM,
Which are?
non-lossy or
Yeah,
lossless.
they're not even compressed. This is all the pixel information. See, that's one frame. It's the same amount of data no matter what's painted in, because it's going to be, it's a grid of 800 by 800 pixels. And it doesn't matter what's written in these pixels, it's all of those pixels. This image is not compressed in any way. It's all the image data, okay? But more of the pixels are non-zero. Most, like in this one, many pixels are non-zero. Whereas in the other folder, the vast majority of pixels are always non-zero. The vast majority of the pixels are always non-zero. Okay? I'm sorry, the vast majority of the pixels are always zero. Here, the vast majority of the pixels are always zero. So this compresses way more. Okay? So the initial amount of data is the same in both folders. Both folders hold 400 frames of pixel data. Okay? And it doesn't matter, you know, if every single pixel in here had a different color, this picture would still be 1.83 megabytes. See? Because what is 1.83 megabytes? It's 800 by 800 triples of ints. You're storing 800 by 800 triples of ints. And it doesn't change. Storing a 0 and storing a 255 is still 8 bits. So it doesn't matter if the pixel 000 or 111, it's still 3 8-bit, it's still 3 bytes. So it doesn't matter if I fill in this whole frame with data, this file is still the same size. It's 1.83 megabytes. Okay, and if you look in the other folder with the pictures that are more complex, notice that each image is still 1.83 megabytes, because that's how many pixels are in that image. There's 800 by 800 triples of 8 bytes each. Okay? Nothing's compressed. So this image file, the PPM file, has the same size no matter what pixels are stored in it. The size of the PPM file only depends on its width, its height, and whether you're storing 3 bytes per pixel or 1 byte per pixel. The complexity of the image does not affect the PPM file. The complexity of the image would affect, like here, let's see. Here's a frame. Save it as a PNG file. So I'm going to save it on my desktop as a PNG file. Okay. It's right there. Okay. Now that was frame number what? That was frame 76. Now go to the other movie and get frame 76. It'll look pretty similar. Okay. See? This is frame 76 and this is frame 76. Now save this one. Now notice that they both start out as 1.83 megabytes, but there's a lot less information in this one. Save this one as a PNG file. Oops. Save it as a PNG file on the desktop. Okay. So I've converted it from PPM to PNG. There's the complex one. There's the simple one. This one, the simple one, is 3,000 bytes. This one's, I'm sorry, this one is, 3,000 bytes, and this one's 42,000 bytes. See, it's almost 10 times bigger. See the difference? This could be compressed way less than the other one could be, okay? There's very little information here. So this can be compressed like crazy, down to 3,000 bytes. There's a lot more information here, so it couldn't be compressed as much. They both started out as 1.83 megabytes. Both frame 76 started out the same amount of pixel data. There's almost no redundancy here. In fact, it's just a sea of black. There's more, there's a huge amount of redundancy here. There's a massive amount of redundancy here because it's just a big sea of black. There's less redundancy here. There's a fair amount. This thing compressed a lot more than a picture of your face would, but it compressed way less than this one did. Okay, so the complex image gets compressed to a larger file. Okay, so a simple image compresses to a small file. A complicated image compresses to a larger file by here a factor of 10. Okay, this is not quite 4,000 bytes. This is over 40,000 bytes. So it's a factor of 10. Okay, that's compression. That's how compression works. Compression, the more complex something is, the less you can compress it. Anybody remember what's the most complicated something can be? When can something not be compressed? What's the most complicated thing something could be?
Each pixel's a random color.
So essentially, what's the most complex something can be? It must be
Totally random.
totally random. Yes. Totally random is as complicated as things can get. You give me a totally random picture, it cannot be compressed. Okay. If you give me a totally random sequence of numbers, it can't be compressed. And this is actually a profound idea in computer science. This is one of the key ideas in complexity theory. The thing that's most complex is the thing that's most random. It's got a name. It's called Kolmogorov Complexity. The thing that's most complex is the thing that's most random. Okay. All right, so you see that here, there's very little sense randomness to this. There's a huge amount of pattern. This guy's a little bit more disorganized. It's a little bit more stuff going on here, so it can be compressed less. Yeah, this is closer to being disordered than this. Okay, all right. So that's everything about this homework assignment. Okay, all right. So create the letters, create the first movie, then do the real interesting step, create that second movie with its post-processing step. And then after you create the second movie, you can turn it into a real, you can duplicate this. You'll be duplicating this GIF file here. You'll just be duplicating this one. Your letters N and W don't have to look exactly like mine. So your animation may not look, your letter P is my P. So that gives you a frame of reference. Your letter P is my P. So like watch the P. But your N and W, if you want to make them look a little bit different, you can go ahead and make the N and the W look a little bit different. So, but since I gave you the P, that gives you a frame of reference. Your movie, your P should follow my P. Okay. And if you want, you can play around with this. One interesting idea is that the post-processing step can really do anything. There's a lot of open-endedness to this. You've got a list of frame buffers. You could actually try to, if you can think of something clever to do with post-processing, send it along. If you can do a second version and try to, if you can come up with something clever to do in post-processing, it'd be kind of fun to see. Because the idea here is I give you 20 or 30 frame buffers. What can you do to post-process them into a single frame buffer? Actually, you could even just post-process the first frame buffer. Like I say, you don't have to post-process a sequence of frame buffers. In a lot of movies, you just post-process one frame buffer by itself and post-process that frame buffer to be something. Like I did an experiment. I did this with one version of your homework assignment. Where is it? Oh, not homework. I'm sorry. Homework 2. The post-processing step was to replace every pixel with a bunch of random pixels. And I decided that wasn't very fun. I decided that wasn't so interesting. Okay, but that was an example of a post-processing step that took each frame, took the letter P, and replaced every pixel with a little cloud of random pixels. So I was trying to, I thought maybe it would look more interesting. With some playing around, maybe it could be made to look more interesting, but right now it just looks kind of silly, okay? But that was a post-processing step that took one frame and replaced every pixel in the frame that was white with a little cloud of random pixels. And the size of the cloud would vary, so you got these kind of weird, I mean, it makes it okay. It's not, it was real easy to write, but I didn't think it was all that interesting. But the idea is that once you have a post-processing step, you can post-process, I'm giving you a sequence of frames and having you post-process the sequence of frames, but you could post-process just one, like that example I just showed you, post-processed one frame into one frame. So the post-processing step was just a single frame. Okay, so and you can do any kind of combination you want. Once you've got a bunch of frames, okay, you got a bunch of frames and you're returning one frame and you're going to save that one frame. How creative can you be in combining these frames into an output frame where you can just imagine doing anything you want? For example, you could try to add color to this movie. Like right now, our renderer doesn't do color, but there's no reason why you couldn't, when you're post-processing the frame, add color to it. So you could add color any way you wanted. So you can make the movie rainbow colored or something. So you could do, if you can do something fun with the post-processing, try it. Okay. All right. So now let's go and talk about what we were doing is we were stepping through this simple example folder in this render. That's what we were doing last week. That's the last thing we did. So let's go back and okay. So that's the example in this folder here. Okay. Now, remember what we did was we literally went through this code line by line and traced it into the scene package. Okay, we went through it line by line and we traced back into the scene package, okay, where we have the camera class, line segment class, model, scene, and vertex class. So we stepped through most of this code. I think we got up to the vertex. So we didn't step. Let's look at one more thing. Let's do this step here. Okay. Now, after you fill up the vertices in the model, after you give the model a list of vertices, then you have to start creating line segments. Okay. So now, what does the line segment constructor look like? So you go over here and see the line segment takes in 2 ints. Okay. Now, notice that there's no default line segment constructor because it doesn't make sense to create a line segment that doesn't have any data in it. A line segment must point to 2 integers. So there is no default line segment constructor. There's only one. Actually, if you notice, the whole class is just one constructor and a toString method. Okay. So the constructor takes in 2 integers and it puts them in its array. Okay. And now remember, what is this doing? The model holds vertices. Yeah. So the model holds there's a vertex. The model holds the idea of there's a vertex and here's a vertex. Okay. So the model holds V1 and V2, and then maybe the model holds some other vertices. Okay, so I can number these things. So this is vertex V0 and vertex V1 and vertex V2 and vertex V3. Okay, so the model would hold this list of vertices. Okay, but which ones do you want line segments between? Like, suppose I want there to be a line segment. Suppose I want there to be a line segment from vertex 0 to vertex 2. So I need to say, so the vertex list, the vertex list the vertex list, it holds V0, V1, V2, V3, V4, okay, right? Now that's index 0, index 1, index 2, index 3, index 4. So now in the line segment list, essentially what I want is first I want a pair that says 0, 2. That's a line segment from 0 to 2. And then maybe I want another pair in there that says I want a line from 1 to 3. Okay. So then there'd be another line segment from 1 to 3. Okay. Okay. So that would describe this picture here. There's 4 vertices and 2 line segments. the numbers in the line segment list, the pairs of numbers are indexes into the vertex list. So 0, 2 means from that vertex. Oh, did I do it wrong? Yeah, from that vertex to that vertex, from 0 to 2. And then that says from vertex 1, the index 1, to the index 3. Okay, so that goes from 1 to 3. Okay, so now what's interesting is when you construct a line segment object and you provide the line segment constructor with 2 indices, for example, suppose I put another pair in here. Whoops. Suppose I put the pair okay. Well, there is no vertex 7 and there is no vertex 8. Those are indices that are out of bounds from here. There's a warning here that this constructor does not check that these indices are valid. That's up to the person building the model to make sure of that. So when you stick 2 indices in a line segment, you have to make sure that they're valid indices. You know, you make sure your code is written correctly. I could have made this thing check, but it really wasn't worth it. It wasn't. It would slow things down, and it would really serve no real great purpose. But it's easy to make the mistake of putting an index into a line segment that's not really pointing at any index in the vertex list. So there's no check when you put something in the line segment list. There's no guarantee that you're actually pointing at something in the vertex list. Same thing's true of all OpenGL and all GPUs. They work the same way. They work with lists of vertices and indexed lists of line segments and triangles. It's entirely up to you to make sure that these indices really point into this list of vertices. If one of these indices gives you an index out of bounds error, your code just blows up. Okay, it blows up at runtime. You know, when it hits this index and it tries to go in here, when the renderer hits that index and tries to go in there, the render is just going to give you an array index out of bounds and blow up. Okay, so there's a warning here that the line segment constructor doesn't in any way check your indices for you. Okay, so here we construct a line segment from 0 to 2. That would be from this vertex to that no, 0, 1. Yeah, that'd be an index from this, a line segment from this vertex to that vertex. Then from 2 to 4, that'd be from this vertex to that vertex. Okay, now what's this thing drawing a picture of? Well, you could plot these points on a piece of paper and figure it out, or you could have the renderer draw it to see what it does. But you know, it's creating something I call a decorated square. We'll see a picture of it in a minute. Okay, so it's a square with a couple extra lines in it. A square would have only 4 line segments. This has got 1, 2, 3, 4, 5, 6, 7, 8. So it's a square with some extra line segments. Okay, I think if I remember right, what it is, it's the end up is a square with line segments going from the middle of this edge to the middle there, then from there. I think if I remember right, it goes like this. It goes from the middle of that to the middle of that, then from the middle of that to the middle of that, and then from the middle of that to the middle of that. Okay. And that's why the square has 8. The 8 vertices are the 4 corners and the 4 midpoints of the edges. And then essentially, this is describing 2 squares, the outer square and the inner square. Okay, so that's what this guy is drawing here. Okay, so create the line segments, create the vertices. Now, what do you have to do? You have to add the model to the scene. So if you go over here and open the scene is holding a list of models, and it gives you a method to conveniently just add models. Remember we talked to you last week about how it's using this ... notation. So you can add models to the model list. That's just a convenience method. Okay. So in this case, we just add that one model to the scene and then render it in the frame buffer. Well, we create a frame buffer to hold the image, and then render the scene into the frame buffer, then dump the frame buffer. Now, starting on Thursday, we're going to start really digging into the render. That's our next goal. Is so far we've been stepping through the scene code. We've stepped through most of the code in the scene library. We've actually stepped through all the code in this scene library. Okay. Then we're going to start stepping through the code in the renderer library. Okay. So we've run out of time, so we have to quit now. Okay. So we're still going to do more on Thursday. I want to shift to these other examples, which are actually more about object-oriented programming than they are about graphics. These other ones make things a little bit more complicated. What happened here? Did I? Oh, I'm sorry. I can't. These examples have to be built from the build script. I keep forgetting that. These examples have to be built by the build script. See, it builds a more complex picture. And there's a little bit of object-oriented programming going on to make it easier to build this complicated picture. It's actually a bunch of instances of that model. There's actually 5 instances of that model here. Okay, so we'll on Thursday we'll go through the more object-oriented examples in this folder, and then we'll start talking about the render, the pipeline, these 3 files here, what make the renderer pipeline, the renderer package, the pipeline package in the renderer. Okay, anybody got any question? We run out of time. Anybody have any question before we quit? Anything? Okay. If you have questions about the homework assignment, of course, send me ask for an appointment or send me an email. Especially if anything seems funny, if there's anything quirky about the homework assignment that seems not quite right, let me know. I wrote it in the last couple days, so it hasn't been. This is the first time I've used this assignment. So if there's anything I forgot to mention, or if there's anything I got mixed up, please, if something doesn't seem right, please ask. Okay. All right.
I have a question about homework 1.
Uh-huh.
Did you receive mine?
Yeah, you emailed it. Oh, I forgot to answer you, didn't I? Yeah,
Yeah.
you sent. Yeah, I forgot to answer you. Yeah, you sent me the zip file. I did get it. I didn't unzip it yet, but you sent me
Okay.
the zip file.
Yeah.
Yeah.
Next time I should be able to submit through Brightspace because I got the.
Well, give it a try. Go ahead. You can go ahead and, just for the record, if you want, go ahead, because actually that'll make it easier for me to grade it.
Yeah, I dropped a class, but your class got dropped instead
Yeah,
of the one that I was
but-
trying to drop.
You should submit this in Brightspace, because otherwise Brightspace will be telling me that you have no homework turned in.
Right.
And then it'll screw up the grade book.
So I can resubmit it through Brightspace if you
Yeah,
want.
yeah. Do that so that it's officially there. Otherwise, it won't show up in the grade book, and I'll have to play games to get it in the grade book. So
Okay.
just make sure. Go ahead and submit it to Brightspace so that it's officially there in the grade book. Okay. All right. Any other question? Anything else?
I also sent you an email about the homework as well, so you can take a look at it.
Oh yeah, sure. Yeah. I had the last 4 days I was doing nothing but writing this homework assignment. I kind of stopped doing anything else for a couple of days to write this homework assignment. It was not easy to, it's a bit of work to write these things. So I haven't been doing much answering of emails for about 3 days. Okay. So yeah, I'll try to get out to all those, but yeah, if you have questions, especially about the new homework assignment or the old one, please write. Anything else?
Nope.
Okay, so I'm going to go ahead and I'm going to stop the sharing, and I'll go ahead and end the meeting. See you on Thursday.